various sampling rate converters like decimators, which is used to reduce the sampling rate. And we talked about interpolators, which we use to increase the sampling rate. And at the same time, we have discussed about I by D sampling rate converters, which in fact can be used to uh, increase or decrease the sampling rate by a rational factor. Well, then we talked about efficient implementation of these decimators along downsamplers and upsamplers along with the filters using polyphase structure. And we talked about some noble identities which in fact help us efficiently implementing these decimators and interpolators. Now what we are going to do is that in today's class, we are going to discuss something called multi-stage implementation of these interpolators, decimators, and sampling rate converters. So what it basically says is that so far we have seen these sampling rate converters. Whenever we talk about D and I, it was always about like we always implemented them as a single stage. Now we will see what are the downsides of having a single stage converter, and then we will.
Sir,
Yes.
కొందరు యాడ్ చేయమంటున్నారు.
Oh God, that new link. Ask them to use that new link. Okay. Actually, I have
Okay, sir.
admitted all. Ask them to use the new link.
Okay, sir.
Okay. क्लास है नंतर नंतर येतो क्लास आहे रे ठीक आहे राहू दे. My God. Okay, shall we continue? Because we
Yes,
are
sir.
running out of time. There is only 40 minutes and we have lost almost 5 minutes already. Okay, if anybody is waiting, ask them to use the new link and join. So I'll be accepting it here. Okay. Okay, I'll take it as S.
Okay, sir.
Okay, sir.
Okay, so as I said just now, today we are going to just a sec. Okay, so today we are going to see the multi-stage implementation of sampling rate conversions. Once again, I'll repeat. So far, we have seen decimators and interpolators and I by D sampling rate converters, all of them implemented as a single stage. But now, well, there are some downsides of doing that single stage implementation. So that's why, just a second. Okay, that's why we go for multi-stage conversion. Uh, yeah, here you can see this particular slide, and here we have the interpolator and decimator both are integrated in this particular structure. And here you can see that, well, the interpolator and the decimator, which are pointed by these arrows, both are implemented as a single stage. So the disadvantage of the single stage is that, well, especially for larger values of D or I. That means if I want to, for instance, uh, increase the sampling rate by, let us say, 100 times and decrease the sampling rate by like a 50 times, then the single stage implementation is a very inefficient method. So that's why we go for this multi-stage implementation whenever we have large values of uh, I and D factors. Okay. Now, for instance, here, one example you can see here, the I by D factor is in fact 130 by 63. So, which means we have to use like a filter, polyphase filter with almost 130 banks. We will be talking about it later. So like that's a very computationally inefficient method. So to prevent and like to increase the efficiency, computational efficiency, here what we do is that this particular implementation, okay, once again, I would like to re-emphasize this particular fact that for large values of I or D, single stage implementation of decimators or interpolators is a very inefficient method. So that's why we are going for this multi-stage implementation in which we divide the okay, in multi-stage implementation, we are going to uh, factor the given whatever the interpolation factor or decimation factor into a product of integers. For instance, let us say I have interpolation factor has 100. So I can write it as 2 into 50, or I can make it 25 into 2 into 2. Okay, so like that we can in fact uh, write and we can divide them into smaller stages. Okay, so which can be mathematically written by this particular product notation, that is pi notation. And well, there is one thing you have to keep in mind, that whenever we are doing this multi-stage, just a second, whenever we are doing this multi-stage conversion, what exactly happens is that in each stage there will be a new sampling rate. Okay, so here that is the expression, this is the expression for the sampling rate at each stage. If here we are assuming that they are like j stages, and the, well, at any point of time the sampling rate at the ith stage is given by this particular expression. Now, well, here we have just below that we have that f naught, which in fact is the initial sampling rate. Obviously, for example, if I want to increase the sampling rate by a factor of 10, so I'll be providing the initial sampling rate, then I'm going to increase it by a factor of 10. So here, as you can see, this is stage 1. This is the like block diagram of that multi-stage interpolator. Here what I have done is that I have taken the large value of I and I have divided it into like various numbers as a product of various integers, and then I'm taking the each small number, I am designing a separate interpolator for it. As you can see, it is pointed by arrow here, that is the stage 1. So since it is an interpolator, we have a upsampler followed by, you can see, a filter. So that filters transfer impulse response is written here. And this is stage 2. Here also, that is the like I2 followed by its impulse response. And here finally we have the nth stage, where we can have that it's a upsampler followed by again a filter. So this is the general structure of dividing an interpolator into smaller sections. So what is the upside of this? What is the advantage of this? Increased efficiency. Because here, well, we will see that, but I'll just give you a small hint here. What exactly going to happen is that since we are using a smaller order, so you will see that the order of the filter will reduce. If you use a single block, the order of the filter will be a very large value, which is very difficult to implement. So here we are dividing it into smaller sections so that we can have better filters. And if you look at this particular slide here, same thing. Now here we are extending to a decimator. So here, let's assume we have a very large value of decimation factor. So I am again factoring it into smaller values of integers like d1, d2, d3, etc. up to dz, and which can be mathematically written by this pi operator here. And well, same thing, more or less same thing here as well. Here also the decimation factor is a large one, d. I'm dividing it into smaller parts, and now I'm cascading all those smaller decimators together. And here you can see I have a downsampler, I have a filter followed by downsampler. Since this is a decimator, we have an anti-aliasing filter which precedes the downsampler. This is for stage 1 and this is for stage 2, and similarly this process will continue for the stages. Well, here as you can see, quite similar to what we have seen for upsampler, each stage will have a new intermediate sampling rate. Okay, so depending upon the decimation factor we choose, since we are dividing it into smaller chunks, so that each section will have a separate sampling rate. Here I have taken an example. If you look at this block diagram, here I'm trying to divide the sampling rate, the decimation factor into two parts. So that's why, as you can see, there are two stages. First stage, a filter followed by a downsampler. Again, the second stage, a filter followed by a downsampler. As you can see, now where the arrow pointing out, here you can see one new sampling rate has appeared after that stage, which is in fact f0 divided by d1. So what is the d1? This d1 is our new uh, that factor which we have just generated. For instance, let us say I have decimation factor to be 100. I can write it as 2 into 50. So now this intermediate sampling rate would be, since I am taking the first d1 to be 2, so the intermediate sampling rate would be f0 by 2. And similarly, the second sampling rate would be f1 by 50, because that's how I am dividing it. Now same, yeah, here one example. Here you can see, here what I have is that I have a two-stage implementation. I would like to implement a decimator using a decimation factor of 100. Since the 100 is a very large number, so I would like to divide it, I would like to divide it into two parts. So what I'm doing here is that I have to take d, this is what has been given to us, this is the decimation factor 100, and well, J is number of stages. You are asked to divide it into 2 stages, and here Fx is our initial sampling rate, which is given as 10,000 hertz. Now here, well, I'm dividing into 2 parts. Yeah, it should have been 2 into 50. Okay, just notice that D1 should have been 2, D2, yeah, you can take it as 50. So 2 into 50, it will turn it out to be 100. Now, first what I'm going to do is that, as you can see, this should have been 10,000 by 2. Just let me just change it to, now this will come as 5,000. Now then we know that D2 is 50. 5,000 by 50, you will get it as 1,000. Sorry, 100. Okay. So this is how we do. As you can see now, there are 2 intermediate sampling rates are there. One is this 5,000, which has come after the first stage of the filter, and this is the second sampling rate, which has come after the second stage, which in fact is our last stage. Okay, now this is how we implement. As I said before, this is to increase the computational efficiency. Now, well, yeah, one more danger of this downsampler specifically is that whenever
In
we
this
down
previous example,
Sir,
D1 is
repeat
also
it once
50.
again, sir.
yeah, pardon me.
In the previous example, the D is 100 and we divided D1 is equals to 50 and D2 is equals to 50. No, sir.
No. This D1 should have been 2. It's you have to express it as a product, right?
Yes, sir. That's
D is
what.
100, so I have taken it as 2 into 50.
Yes, sir.
Sir, you just explain it once again, sir.
Yeah, right. So here, as you can, once again, I'm here we have a decimator. We would like to implement it as a two-stage by two-stage process. Okay, just a sec. Well, okay, here the information what is given to us is we have been given D as 100. So what is D? Here it is the decimation factor, and J is 2, that is the number of stages, and Fx is the initial sampling rate. And we want that to be reduced to by a factor of 100. As I said earlier, this 100 is a huge number. If you implement it directly by a single stage, well, it would lead to a very inefficient implementation. That's why what we are doing is here we are trying to implement as a two-stage implementation. In two-stage implementation, we are going to write the 100 as a factor of 2 integers. So 100 can be written as 2 into 50. So my D1 is 2, D2 is 50. Is it clear?
Yes, sir.
Yes, sir.
Right. Now, as I said earlier, since I have 2 stages, out of each stage, I will get a new sampling rate, and which depends on that particular factor. Now, for first stage, as you can see here, the incoming sampling rate is 10,000. So, which is the initial sampling rate. Now, that incoming sampling rate, as you can see, the first decimation factor, I have taken it as 2. So 10,000 by 2 will come out as 5,000. So that is the sampling rate which I will get out of the first stage. And here you can see now this 5,000 we are feeding it to the next stage. So what happened? So for the next stage, what is the D2 factor? So D1 was 2, D2 is 50. So again the sampling rate will reduce by a factor of 50 here. So earlier it is 5,000 which is being fed to the second stage, and it is getting divided by this factor of 50. So here it is coming out as 100. Even if you divide 1000 by 100, 10,000 by 100, you will get it as 100. But same sampling rate we are going to get, but we are using this multi-stage approach for the sake of efficiency, right? Is it clear now? Okay. Well, as I said earlier, whenever we talk about decimation process, we have to consider the aliasing effect as well, because whenever you decimate the sequence by a certain factor in frequency domain, the frequency components will spread or they stretch. So there is a danger of aliasing, that is overlapping with the adjacent frequency bands. To prevent that, we have to take care of certain parameters here in each and every stage of this multi-stage arrangement. As you can see, in every stage we have a filter, right? So by appropriately tuning that filter to not to send frequencies which otherwise would break the Nyquist criterion, we can avoid the aliasing effect. And here you can see this is the desired specifications. Okay, these are the desired specifications of an overall decimator. That means if you would implement it by a single stage also, these are the specifications. So what are the specifications we have? We have pass band cutoff, we have stop band cutoff, and ultimately the third one is what? The maximum frequency, the stop band cutoff, how much it can be. So these are the specifications which are given for the overall decimator. But we have to now we have to design this multi-stage each and every filter in such a way that there will be no aliasing effect. And first, yeah, you have to memorize these three expressions. Okay, so these three expressions, out of which the first expression is the pass band. It belongs to the pass band, which does not really change from stage to stage. It will remain the same, but what changes is the transition band. In transition band, now the transition band earlier was extending from f, that pass band frequency, to the stop band cutoff. But here what happens is that now we have multiple stages. So each stage is getting a new sampling rate, right? So as a result, what happens is that for each rate, each stage, there will be a new transition band cutoff frequency, which is given here as Fi minus Fsc. And well, from the previous discussion, it is clear that what is Fi? That is the sampling rate out of each stage. If it is a first stage, we have some sampling rate, some new sampling rate coming out of it. For the second stage also, we have some new sampling rate coming out of it, and so on until L stages or J stages. Similarly, the stop band frequency will also change here. Okay, so by the almost the same factor, but here what happens is that the stop band frequency, the upper band of this stop band frequency will be the Fi minus 1 by 2, which means that the previous sampling rate divided by 2, previous stage sampling rate. If Fi is the current stage sampling rate, Fi minus 1 would be the previous stage sampling rate. So these are the things you have to keep in mind whenever you are trying to design a multi-stage decimator or interpolator. Does not really matter. The procedure is same for both. And moving on to the, well, here some of the identities I want you to know. So these are simple identities. Now here whenever, now the highlighted diagram, you just have a look at it. Whenever you have two decimators in cascade, well, they can be replaced by a single block with their multiplication. Okay, and similarly here, same goes for the interpolators as well. Whenever we have two interpolators, this is one interpolator and this is another interpolator, first interpolator, second interpolator. When they are in cascade, you can replace them by their product here. Okay, we have kind of done opposite to this in a previous discussion. We in fact had a big decimation factor or a big interpolation factor. In fact, we have divided into smaller chunks and we kept them in cascade. Okay, this is kind of opposite to it, and this is a vice versa thing. So that means D1, D2, well, they can club it into D1 into D2, or they can divide it into separate sections of D1 and D2. Now, well, this is important. Now we will come across situations where we have a sampling, upsampler comes first, then we have a downsampler, and the factor both are equal. For instance, if upsampler is 100, the downsampler is also 100. So what exactly happens to the signal? Nothing. So what we are basically doing is that we are upsampling it by 100 and then we are downsampling it by 100. So as you can see here, the output signal is in fact input signal. And I would like to remember this particular identity because this is very important when solving the problems. And here, whenever we have a upsampler followed by a downsampler of same value, well, they cancel each other. Here you can see that they in fact canceled each other. There is no block at all, right? Well, we have only 10 minutes left. Okay, now here, well, same thing can be explained using a MATLAB. Here you can see the original sequence. I have upsampled it by a factor of 2. So that's why, as you can see here, since the upsampling factor is 2, 2 minus 1, 1. So a 1, 0 is stuffed between two successive samples. When I again downsampled it by a factor of 2 again, as you can see, the input sequence and the third sequence, both are in fact same. So that means whenever an upsampler followed by a downsampler of same value, they cancel each other. So why I am saying it is important is that because, just a sec. Because, well, this is opposite to it, but this is different. Here what we have is that we have a decimator first or a downsampler first, and it is followed by an upsampler. But here they don't really cancel each other. Okay, this is very important. So for an upsampler followed by a downsampler of same value, they cancel each other. But whereas a downsampler followed by an upsampler, they don't cancel each other. So the output would be something like this. So we have some values which turn to be 0, which were not there in the original sequence. So here, as you can see, there is no net expansion, which means the number of samples, if there were 100 samples, there will be 100 samples. But what happens is that the sample values will change. And you can see here in this particular MATLAB example. And well, this is the original sequence. Careful. This is the original sequence. Now I have downsampled it, and now here you can see that certain samples have been disappeared here, again I have upsampled it. But if you look at the first sequence and the third sequence, they are not the same. Well, the number of samples are same, but instead of especially this particular sequence, now which is being pointed by this black arrow, which is not there in the third sequence. Once again, this particular sample here it is not present. That means its value is changed to 0. That's why a downsampler followed by an upsampler is not same as an upsampler followed by a downsampler of same value. So that's why for an upsampler, downsampler followed by an upsampler, we have to use this particular expression. The original samples will be present only at the integer multiples of this I or D, since they are same. But at other places, we are going to have 0 samples. Okay, you have to keep that in mind. If you want, you can copy this code into MATLAB. You can play it around with. And this is one more example which is important. Now here I have one x of n, y of n relationship. Here this is a multi-stage arrangement. Now I am asking you to find its how does its output would look like. Here what happens is that now I have first I have 4, which is an upsampling. Then I have 12 as downsampling. Here I have 3 as upsampling. As I told you before, a upsampler followed by a downsampler will of same value will cancel each other. So in the middle, I have something called 12. And now I can write 12 into 4 into 3. So here you can see I have divided the 12 into 4 into 3, and this particular, which is in brackets, here you can see I have an upsampler which is followed by a downsampler. As I told you earlier, they cancel each other directly. You can simply remove those. But here, after that, what's happening? I have a downsampler followed by an upsampler. So you can't really cancel them out directly. Instead, the samples at the output will appear only at those points which are integer multiples of either I or D, which is 3 here. So what are those integer multiples? 0, plus or minus 3, and plus or minus 6, and then 9, and so on. At those points only you will see the samples, real samples. And at other points, like in between 0 and 3, we have sample number 1, sample number 2. Those will appear as zeros. And then we have sample number 4, 5. Those will appear as zeros. What I recommend you is that you take this example and you try to implement this in MATLAB. Okay, you take one sequence, downsample it by 4, then upsample it by 4, then downsample it by 12, and then try to upsample again by 3, and you just try to see the difference between the initial sequence and the final sequence. You will see the difference. Okay, and well, we are running out of time, so if possible, I would like to schedule one more video today. Is it